Welcome, and thank you for joining us for this webinar presentation. We are the Defense Systems Information Analysis Center, or DSIAC, one of 3 IAC domains in the DoD Information Analysis Centers operating under the Defense Technical Information Center, DTIC, within the Office of the Undersecretary of Defense for Research and Engineering. Our informative webinar series highlights current and emerging research and technology developments. It presents an opportunity for accelerating the DoD's leverage of these advancements by increasing awareness and fostering technical collaboration. DSIAC serves as one of the premier information research partners and curators of technology advancements and trends for the defense systems community. As such, our organization supports those working in the defense systems domain of DoD research and engineering. We do so by helping navigate the vast landscape of scientific and technical information, allowing our customers to get a head start on their technical projects. With an understanding of the defense systems DoD research and engineering landscape, we provide research and analysis services. We help unlock access to information, knowledge, and best practices from government, industry, and academia to stimulate innovation, foster collaboration, and eliminate redundancy. We hope you enjoy this webinar presentation and that it serves as a catalyst for community collaboration and improved DoD defense systems research.
All right. Well, good morning, good afternoon, good evening to everybody who is joining us. Appreciate you dialing in or joining us for this webinar presentation by Evan and Rob. Before we get started, I'm going to go through a couple administrative pieces for the webinar and give you some introduction to the system. So my name is Brian Benish. I'm the domain lead for DSIAC, the Defense Systems Information Analysis Center. And as mentioned, this is one of our monthly webinar series as an opportunity to share work that's being done by the DoD research community with you to help foster some collaboration and innovation. And so we're happy to have Evan and Robert with us today. If you are in the WebEx platform, I just want to draw your attention to a couple things. First is the Q&A section. You may have to click some ellipses, little 3 dots somewhere on the screen, depending on whether you're in the full application or the web application. But if you search for the Q&A section, that's where at any time during the presentation, if you have a question you'd like to get in order, go ahead and enter it into that the queue there. I want to distinguish that from the chat, which is a separate feature if you want to interact with us. But again, the questions are where the Q&A section is where we're going to ask you to put your questions at any point during the presentation. After the presentation is concluded, I'll chime back in here and moderate the Q&A, and we'll go from there. If you have any technical difficulties during the webinar, rest assured we are recording this. And additionally, the slides are now available on the website, so you could head on to the website, the DSIAC website for this particular webinar, and download the slides to follow along. And I think that concludes the main pieces for the introduction of the system. So let me introduce Evan to present for us today. So Evan is part of the Ground Vehicle Materials Engineering Division at the Army's CCDC GVSC. I'm not going to hit all those letters, but the last part being the Ground Vehicle Systems Center. He researches blast and high strain rate behavior of composite materials for structural applications. And he has researched the dynamic response of shock-loaded composite metal hybrid panels under pseudoblast loading induced by a free piston shock tube and applied his expertise to CCDC GVSC. Dr. Patton, he holds a PhD in mechanical and civil engineering from Michigan State University. And so we are very pleased to have Evan with us. Rob also is joining us for this presentation and will be a co-presenter on this, and we'll chime in if need be, but primarily presented by Evan. So Evan, I'll go ahead and mute myself here and let you carry away from here.
Yeah, thank you very much. As stated, I'm from CCDC GVSC. Quite a bit of a mouthful. We're a subset of the Army branch under AFC, which is Army Future Command, and the CCDC GVSC stands for Combat Capabilities Development Center, Ground Vehicle System Center. So I'm over in Warren, Michigan. I'm on the materials side. This presentation's from actually my GBSETS symposium, which is kind of like our internal conference. And that is the manufacturing, modeling, and characterization of thermoplastic composites for military ground vehicle applications. So to start, why structural thermoplastics? Well, I mean, it's no secret to anyone that defense and automotive industries seek lightweight material solutions. Why? It not only increases mobility, but fuel economy in the vehicles. That benefits both sectors, obviously in different ways, but they say that they share that same common goal. It also frees design weight for additional upkitting. We shave off, say, 500 pounds. That means we can put 500 more pounds of robotics on it and help modernize that vehicle fleet. So it's kind of nice in that aspect and admirable. And to do this, you know, composites, they have many benefits, not only being lightweight, but they all have high strength and specific stiffnesses and high capability for energy absorption. So just to start things off with some basic examples of a thermoplastic utilization in a ground vehicle system, there's two case studies. One on the left-hand side here, it's a tactical cargo shell. This was basically just a prototype part to show that we can produce a vehicle part that is lighter than its legacy material. In this case, it was 35% lighter than its aluminum predecessor. In the middle here, we have a theoretical vehicle combat floor. This is just a generic shape, but this is just to show that, you know, we can obtain things up to 56% lighter than just a baseline aluminum design. So getting to that point where we actually start prototyping and fielding things, there needs to be some housekeeping stuff. And that's just because thermoplastics can be extremely complex. Basically, that all kind of stems from the manufacturing process. And in the manufacturing process, we actually introduce a lot of variability within a material. And that's due to the processing temperatures, such as the heating and cooling rates, and that'll define crystallinity within a material. The consolidation pressure as well, that does have some influence on crystallinity, and then the dwell time as well. And kind of like a subset of the manufacturing specific properties, we have defects such as fiber wash. And fiber wash occurs in a sample when, say, you have a mold with a little bit of air void from maybe a tolerancing issue or things like that. When the resin, in this case thermoplastic, is molten, it'll want to flow and fill that void, and it'll actually drag some of those fibers with it, causing resin-rich and fiber-rich areas, as well as off-axis fibers. So it's really important to kind of have a manufacturing specific mechanical characterization so you can then feed your finite element models a more accurate representation of the material you're actually using. So this whole, I guess, webinar and conference was based around a case study where we set to do exactly what it kind of says: manufacture, characterize, and model a thermoplastic composite. In this case, we chose a PET glass fiber composite. Why? Well, PET was a good candidate for manufactured specific composite properties. It could either be semi-crystalline or amorphous, depending on how we cool it. And it's a unidirectional tape, and for those that are kind of unfamiliar with composite, unidirectional means exactly what it kind of implies. All the fibers are running in one direction, and this picture here to the right is a good representation of the material that we are using. And you can see kind of these striations in the material. These are those actual fibers, and they're all running in the tape direction. And to manufacture our test objects as well as our characterization test samples, everything was conducted using a hot press consolidation method. And I'll talk a little bit more of that on the next slide. The characterization process, kind of couples with the modeling part. We implemented an LS Stein material 54 card, and that drove the characterization demands such as tensile properties, compression, shear, and interlaminar properties. So to touch back on the manufacturing process, what we see here in the center is a hydraulic hot press. And essentially this giant platen here is driven down by this piston with, I think, the capability of about 150 tons. And what we see on the left-hand side is the manufacturing stack up, or sandwich as we called it. And that's essentially an upper and a lower aluminum call plate. These basically just acted as sacrificial platens just in case something happened to the mold. And those are then bounded by a aluminum picture frame, which helped confine the composite that's here in black into its final shape. And these layers of Kapton film were just implemented for release from the mold. And that sandwich stack up was then placed into the mold, pressed, and it followed the manufacturing schedule here on the right, which is a preload of 35 tons of force. It's then heated to 510 degrees Fahrenheit, which is above melting temperature. And it was dwelled at 510 degrees Fahrenheit for about 15 minutes. That's just to ensure that the entire composite was liquid at that point, molten. And then at that point, at the 15-minute mark, it begins to cool. And it's kind of hard to see in this picture, but there's a water-cooled chiller in the back. And that actually pipes conditioned water through these platens to cool them down at a relatively fast rate. We calculate it's around 59 degrees Fahrenheit per minute. That's driven by the capacity of the machine. So that's not by design or anything. It was just a characteristic of the setup that we had. So we just went with it because we weren't doing a crystallinity study on it. Before I dive too much into the characterization results from the specimens that were pulled from that hydraulic press, I think it's important to kind of highlight the difficulties of dealing with this material. And I shouldn't say that it's just prone to this material in general. It's just all composites. But I'd like to highlight specifically our tension and compression specimens led to a lot of premature failure in the tensile mode. And we saw that in essentially shearing in the gauge or in the grip areas from the Instron machine. The composite was so strong in the tensile direction that it would actually pull on the grips to the point where it crushes the composite in the tabbing area and would lead to a premature shear there. And then there's also an issue with off-axis fibers. So I kind of refer to it as almost like piano string, because when you pull these specimens in tension, you can kind of hear plucking from each individual fiber rupturing. And that's simply due to some of the fibers being under a higher load just because of the way it was manufactured. And if you think about it from a metal standpoint, you're pulling the entire material at the same time. So it's a very representative sample of what you're seeing. But with the composite, you're pulling on all these fibers. And if some of them are carrying more load than others, it's not necessarily indicative of the load that it's actually carrying or can carry. So we needed to implement a strategy to kind of get around that piano string, which led to localized cracking within the specimen itself. And to do that, we implemented DIC to obtain a local failure strain to back calculate a theoretical failure stress, because that's what we're ultimately looking for. And then the compression specimens, simply put, we needed pristine axisymmetric specimens. Commonly prismatic rectangular specimens are used, but in order to manufacture those, you need 3 different planes of symmetry, both the top, bottom, and the sides, all 4 sides. So to kind of get around that, we figured what better geometry to choose than a cylinder, because you only have one face to really worry about. So to do that, we chucked it up in a lathe just to see how the material would kind of machine down. And we got a really good surface finish on it. It actually machined quite well. and led to some good representative samples, which I guess since we're talking about them are shown here on the bottom right. These are failed specimens. The one on the left, the fibers are going up and down, and the one on the right, the fibers are essentially coming at you if you're looking at your screen. So we were happy with these failure modes. And then moving over towards the tensile specimens, the left kind of shows that piano stringing type of failure. Here, the fibers are actually off axis. So as that specimen was pulled, these fibers wanted to straighten out and follow their load path, causing these frayed edges here because the fiber axis was just ever so slightly off kilter. So to kind of combat that, we did that DIC methodology, as I mentioned earlier, where we essentially looked at the DIC footage and tried to find a really nice representative area where we did have a crack appear across the specimen, even if it wasn't completely across the entire one. As long as it was across a localized area, we were happy with it. And what we saw was that we had a pretty linear response, which we kind of expected, and then all of a sudden a failure. And we were able to obtain a failure strain and then back calculate it with the linear elastic moduluses, as we saw in this graph here on the top left. We were able to obtain a localized theoretical stress limit. And I threw some more graphs up here. This top one is the 0 direction. Bottom is the 90-degree direction, which you're pulling, I guess, the fibers apart from each other. And then the right-hand side are both the 0 and 90-degree compression tests. I don't want to focus too much on these. I just wanted to show you the consistencies and kind of go through the elastic part of the data. The more important aspect of this slide is the tabulated data on the left-hand side here. And what you see plotted here is the manufactured spec data compared to our experimentally derived mechanical characterization data, as well as like differences between the two. And this is like probably one of the more important points I want to make, whether it be with composites or any other material, is that there's quite a bit of mechanical variance in the mechanical properties between these two. And it's important to capture that in your model because this is manufacturing specific. So this is everything you're doing and capturing in your material, quote unquote, and it's going to be representative of how that experimentally tests, even if it is different from the manufacturer. And another important point to make is that some of these were so far off that we actually contacted the manufacturer to say, hey, what are you guys doing to, get this value you had? And ironically, they didn't have an answer because they didn't test it. Some of these values reported are theoretical, and I know I'm sure I have some theorists in the audience, and they're going to kind of grind their teeth at me, but theory doesn't always translate to experimental results, and this is kind of one of those cases. This theory is based on it's called multi-mechanics, I believe, which is a representative volume element, which you feed it a bunch of different properties for the individual fiber and the individual matrix, compound it into one system and do a virtual tensile test or compression test on it and get these results. So it's very idealized and nowhere near close to an experimental setup. So it's also a very important point to make where if you're blindly throwing in these values, you're playing with fire there for a little bit. So it's a pain to experimentally derive those mechanical properties, but in the end, it's going to be worth it for when you start to implement those into the model. And as mentioned earlier, I did utilize LS Dyna, specifically material card 54, which if you're a composite modeler, you probably are very well familiar with this. But for those of you who aren't, the figure on the right-hand side, the graph, is a good indication of what's going on behind the scenes. And essentially what it is you feed it your mechanical data, and there is damage softening parameters such as this slim C2. And what it basically says is that you have your linear elastic response, and then you hit that failure limit, which you determined experimentally. And then upon hitting that limit, you then drop to a, this is actually a percentage of the strength. And it essentially will carry load up until a very final failure strain. And once it hits this final failure strain, it completely deletes the element. There's no other load-bearing significance of that element. It's just non-existent and gone. This material card is unique because it does account for failure modes such as fiber buckling or fracture, matrix crushing or fracture, and another one, this is actually separate from the material card itself, but for this case study, delamination was also kind of assessed. And to look at that, behind the scenes, there's this mathematical formulation. Basically, what we did was we characterized both the normal and shear forces at failure, and you put it into a nodal tie constraint. And this formulation here says I'm going to probably butcher this mathematical description, but the squares of the normalization, the sum of those, if they're greater than 1, it is considered a failed node, and those initially tied parts are now independent, and they're allowed to kind of do whatever they want, which is important in a composite because delamination is typically leads to a degradation in strength. So we want to assess those delamination areas as well. And when we input our mechanical characterization data, this is what we input into the system. And those gray boxes kind of highlight everything that we experimentally derived. Everything else is either a geometric property that tells LS-Dyna which way the fibers are going and how the model is going to accumulate damage, such as these parameters here. And that kind of tunes your model to what you see experimentally. So this model essentially is a representative model instead of a predictive model, although it can kind of get you close if you're familiar with the material and the behaviors of the material. So the overarching case study, the test objects, were essentially a hybrid panel. It was a stack of that PET glass fiber composite that was glued to an aluminum face sheet. And these panels were, and I apologize, I don't have any experimental results or figures or anything like that because I didn't want to dive too much into that aspect. But basically, we set those test objects in a open-ended blast tube, and we tested it with this pressure curve here. This pressure curve was both experimentally recorded and modeled in LS-Dyna. What you see on the right-hand side here is a pressure distribution contour map of the actual specimen. And those specimens were, I believe this is a 7-inch circularly, fully circularly clamped specimen, with the nozzle obviously being right in the red area. That pressure was then allowed to distribute through the material. And what we're able to do with that model is look at the real-time stress state of the material. On the left-hand side, this is a composite ply, a singular composite ply that is just before failure. We see the red area is experiencing a stress state of around 714 megapascals. I think our failure limit for this material was 960. And then a few milliseconds later, that stress limit's reached, and that strain limit is also hit, and essentially starts eroding the middle of that composite, and thus completely eliminating all composite, quote unquote, in that area. Realistically, this section isn't going to be or is going to be intact in the actual specimen, but for the model's sake, this void area is the damaged area. This is the non-load bearing structure, and so forth. These two plots here, this is the delamination of a specific interface between two composite plies. Red is bad. Red means that it is delaminated. Blue is good, meaning it's still acting as essentially one system. And the two different plots, I wanted to add two different ones for the point that the one on the left is at peak deflection, and the one at the right is sometime after when we pulled the specimen out of the test chamber, and there's no additional loading. And I just thought it was an important point to make, that even though we're past the peak deflection, there's still some damage accruing within the composite, and that just is part of the nature of a high strain event where we kind of have damage even after that initial peak. This figure here indicates a cross section of that hybrid panel. The brown is an aluminum face sheet, and the multicolored areas is adhesive and composite plies. And this is just a time progression through to kind of show the extent of the delamination. You'll see that it begins with an area of high localization deformation that gradually tapers out. And in this figure here is when you actually see an initial delamination site here, which progresses throughout this entire composite ply, eventually completely delaminating, as well as having extensive delamination throughout the composite until it finally settles back into its final deformed state. That is, for lack of a technical term, fluffed up, where all these composite plies are kind of delaminated, just kind of laying on top of each other. So all in all, we had really good validation between the experiment and our model. And that was solely attributed to a very rigorous mechanical characterization. If we were to have taken those manufactured spec properties to determine the model, I don't believe we would have been anywhere near the correlation that we were able to obtain between the two models. And basically, it's just to kind of highlight, and I guess this slide does a good point synopsis of everything, where thermoplastics demand manufacturing specific characterization. I mean, that's just because they're kind of messy to deal with. They're picky with how they're heated and cooled and consolidated, and any two people can get wildly different results. So it's very important that your entire manufacturing process is documented, well recorded, and representative of what you're actually going to be testing. And that way you can kind of account for these resin and fiber rich areas, the crystallinity, fiber drift, all that sort of thing. So with that, that's all I had today. I'm not sure if I'm short on time, long on time, but I'd like to thank you all for taking time out of your day or your lunch break and attending the webinar. And I believe there's Q&A chat. So if you have any questions, I'd be more than happy to answer them.
Yeah, absolutely. We did get some questions that came in. Rob actually answered a couple of them, but maybe I'll just, I don't know if you can see them or not, Evan, but I might
not.
Okay, yeah, I was just going to re-ask those questions and tell you what Rob said, and if you wanted to add anything else, you could.
Perfect.
So first question came in, said didn't catch it if you said, but for the mold compression stack, is it also under pressure within a vacuum bag? And then Rob said in the process, the pressure was applied at positive pressure from a hydraulic press, and there was not additional vacuum applied to the material.
Yep, that's correct.
Yep. Then there's a question about defining DIC, digital image correlation, as Rob answered, which uses cameras to track the movement and strains developed in the specimen as it's being tested.
Yep.
All right, unanswered yet question is asking, says for the tensile testing, how did you decide on the sample geometry? Would it be more standard, or would more standard dog bone shaped samples not work well with the type of laminate?
Yeah, exactly. So with composite specimens, most of them are defined within, I think it's ASTM B3039. And that all indicates the size and width and gauge thickness, I believe, of the composite specimens that you're testing. For this case, we're dealing with the unidirectional composite. So if you think of a dog bone shape, and if the fibers are running up and down, you're going to have the fibers going through the gauge section, going up into the tabs. Those are going to be your load-bearing fibers, and the ones on the outside, if they're terminating kind of on the sides of the gauge length, they're not going to have any load-bearing capabilities. So when you pull the specimen, you're actually just going to kind of shear that middle section out. So that's why a dog bone is kind of avoided in this circumstance. I think for like a woven fabric composite, it might be a little bit better, only because it'll help bind those fibers in the transverse axis in the grips from kind of spreading apart and experiencing kind of what we saw in this circumstance. But for the unidirectional, a dog bone was kind of avoided just for that.
Okay, good, thanks. The next question was asking, what's the driver for using thermoplastic composites versus traditional thermoset composites for your applications?
Yeah, so the thought of using a thermoplastic composite over a thermal set is recyclability. So there's a theory out there that say, for example, and this is, I know, like reflection of what we're actually looking for. Like a ballistic standpoint, you shoot a block of plastic with a thermal set that's a chemical reaction, you can't really repair it. For thermoplastic, the theory is you can heat it back up and it's good as new. So there's a little bit of repairability, recyclability there. From a formability standpoint, the thought is that thermoplastics can be essentially stamp formed or even injection molded if you're looking at discontinuous fiber, leading to increased production times rather than having an actual mold for thermal set, laying your fabric, injecting the resin, and then waiting for that to cure. So there's applications where both kind of shine. This is just a subset of kind of like a what if. So that's kind of why we looked at a thermoplastic in this case. It's just, what if we start looking more heavily into these thermoplastic composites?
Mm-hmm. Okay, good.
Evan, can you hear me?
Yep.
So this is Robert Hart, co-author here. I was just going to make one additional comment. Some of the other reasons why we're looking at thermoplastics within the Army for ground vehicles is the ability to process these. We can do at much faster cycle times. Evan's been a part of a project just recently where we were able to make a thermoplastic composite for approximately $500 in a matter of 10 to 15 minutes versus a thermoset where the alternative was about $2,700 and took about a day for that total process. So there are some real advantages in terms of cycle time and potentially cost, as well as some performance benefits such as toughness and things like frag performance of thermoplastics.
Perfect. Yeah, thanks. And we just got a quick question maybe tagged onto that was just asking if that same theory could be applied in materials for UAVs for reducing weight on that platform. I know that's not necessarily part of the ground vehicle center, but
yeah, no, absolutely. And I guess it kind of leads to a good, I guess, discussion point where a UAV obviously doesn't necessarily, it's unmanned. So when we're introducing new materials, this might be more of like a gateway for these composites, because the Army specifically isn't necessarily as familiar with implementing them in their ground vehicles. So there's a little bit of hesitancy introducing these types of materials in a manned system because, you know, of the what if. So for UAVs, for sure, I know the Air Force is definitely looking at, you know, composites in that aspect. And for thermoplastics, I think I see your questions kind of coming in. From a formability standpoint, yeah, absolutely. The outer shell, everything about it can be formed out of these materials, especially for thermoplastics. When we're talking about either discontinuous injection molded parts or even three-dimensional chopped fiber printed parts, you know, from a regular 3D printer, or in this case, a giant 3D printer. So I hope that kind of answers your question.
Yeah, no, I think it answered multiple questions related to that, so it's good.
Perfect.
All right, another question was asking if you've done any comparison between the fabrication processes. So maybe, for example, do you get different property differences between autoclave, press, and in situ tape placement?
So we haven't done like a study on the variance between manufacturing processes, but I think like the underlying notion of this kind of like addresses it, that each manufacturing process is definitely different. And it'll give you different material characterization data. So regardless of your application, you definitely need to kind of run a characterization study depending on what you're doing to make these parts.
Yeah. All right. On the topic of the Ellis-Dyna simulations, what element size and type, shell or solid, did you use for this?
These were all solid elements. And the reason I chose solid was I wanted to see if there was any through thickness shock within the material, as well as I believe model the delamination. And you can do that with shell elements, but I think it's a little more complicated. And then the element size I'll go back a couple just to kind of give you a general sense. This is a 7-inch diameter. So that would be, oh gosh, 180 millimeters, I believe. So each one of these elements, I believe, is about 2-3 millimeters. Actually, it is 2.82 millimeters square for the most part. I know some of these are rectangular and triangular, but the general length is about 2.8 millimeters.
Okay, gotcha. Well, and a question just came in kind of on the topic, the simulation part at least. Does the correlated material card performance, does that hold when you're applying to a larger mesh size to be used in a full vehicle simulation?
That's kind of the tricky part, because if you're dealing with a larger element, that element's going to erode if it hits quote unquote failure. So obviously there's going to be some kind of mesh sensitivity, especially when you're talking about damage and what kind of damage you're expecting. In this case, we didn't really know what we were expecting, but from a 3 millimeter mesh size, we figured that would kind of be very representative of a localized area of damage. But for a vehicle, obviously computation's a huge concern with the how large the area is. And I think for this case study, or for a vehicle case study, you're going to be looking at more of an individual component rather than an entire vehicle, solely for that reason.
Right. Yep, makes sense.
Yeah, one comment I'll add on to that. When it does come to the simulations, a lot of the really detailed analysis we do is more on the component or subassembly level. But we do have a group here that's able to fully integrate these type of models into a full vehicle blast simulation. So we have done that a handful of years back.
Oh, good. Okay. Let's see. Next question. Oh, have you done any work with the IM7 Peak as material. Comment just saying that work has been done to show some superior blast resistance with that material in the structure.
Yeah, so dealing with thermoplastics, especially with some of the companies in industry, PEEK's definitely one of the more higher engineered plastics. It's unfortunately a little too expensive for us when we're talking full vehicle structures with the thicknesses that we're kind of looking at. It kind of becomes impractical as far as utilization, because at the end of the day, we're going to have to be cheaper than whatever legacy material it is, which is typically either like aluminum, steel, titanium even, and composites are already pretty pricey. And implementing a PEEK or a PEC, it's definitely out of our case budget. Yeah. So we try to avoid those for that very reason, which is kind of unfortunate, but yeah.
Okay.
Yep. I will add on to that one as well. So when it comes to PEEK, PEC, and PEI materials like that, we have investigated those, but again, like Evan said, for the type of applications we have, the performance and like temperature capabilities of those materials, we have a hard time justifying. PPS or polyphenylene sulfide seems to be about the highest performance material. It seems to make sense for us in like structural applications in terms of like the moderate to higher end thermoplastics. But that's why like PET or PPS have good applications for us, because they have some flammability resistance or heat resistance, but they're more at an accessible price point to where we can use them in relatively heavy structural applications.
Mm-hmm. Makes sense. All right, thanks, guys. All right, the next question was asking about the void content of the tape that you used. Do you know what that was?
From the factory, we didn't calculate a void content. One, because it's relatively thin tape. I think it was 0.26 millimeter thick. And secondly, the amount of voids within the material pre-processed isn't necessarily a concern as the void content after. If we look at, I did have some microscopy images here. There is, and again, there was no void content assessment, but we looked at the microscope images and we were pretty happy with the consolidation results, seeing that there wasn't as much void, if any, within the material. So we kind of just left it as that because we were, again, just characterizing the material as manufactured. So we weren't trying to idealize the material by any means, whether, putting it under vacuum to pull out any voids. It was just kind of left as is. But from these images, we were pretty happy with how the composite was manufactured. So we kind of just left it as is.
Okay. And we just got a question somewhat related to that, asking if you had any challenges with the bonding or the joining of the thermoplastic composites for your applications.
Yeah, this material was pretty tough. I shouldn't say tough to manufacture because it was actually quite easy. Its inner laminar properties are relatively low, and I wish I did have the normal and shear values that were obtained here. I think the normal, so essentially this was just a butt joint where it was a rod of material that was pulled. And this is through the thickness. So you're pulling essentially the plies apart. And that was only about 4 megapascals. And then we did a lap shear joint, which was actually trying to test the adhesive used to bond the aluminum to the composite. It was a lap shear joint to see that strength, and we were trying to get the interfacial strength from the composite, and it actually sheared in the composite. So the interfacial shear strength of the adhesive in the composite was stronger than the actual composite with itself. So that was one of the tricky things with this material, and that's partially due to the unidirectional nature of it. You know, there's such a high difference in the anisotropy within the material. Your x-axis is much stronger than your y-axis, and you can pretty much see that in these properties here, the moduluses and the failure strengths. So that made it pretty tough to deal with.
Gotcha. Okay. Thank you. Let's see. How about could you speak to any efforts that you might be undertaking to evaluate, either by measuring or modeling, the spectral signatures of the materials, maybe the infrared in particular?
So our group doesn't necessarily assess any of that. I believe that's more of we have a survivability group, and they'd be the ones looking at that assessment. So I don't know if Rob wants to speak anything on that.
Yeah, sorry. We are not actively investigating signature on these materials. The specific material Evan is working on, and some of the other ones, like I mentioned, PPS composites, we are looking at for interior applications. So signature is not as critical there as it would be, obviously, for an exterior structural application.
Okay. Fair enough. All right. You know, I think, all right, yeah, let's do one more question that one big one that I have to get to before the end, and I don't want to forget it. Next question that came in was asking if you could speak to the test setup for the compression testing, and then following was saying, do the laminate designs have strain rate sensitive performance like other plastics?
Yeah, so for the compression test, it was pretty simple. It's an unconfined compression test. So essentially, these specimens here are loaded between two platens, kind of like you saw in the hydraulic press, and it's squished between those two flat faces. And there's obviously a load cell in which you obtain all of the mechanical data. And then as for strain rate dependency, this particular material has not been assessed for strain rate dependency. But what we are seeing is that a lot of similar polymers and fiber matrix systems are experiencing some strain rate sensitivity, especially when you start getting in the order of magnitudes of those seen in like a higher strain rate event, like a split Hopkinson board and things like that. So,
all right, okay. All right, well, I think that covers all of the technical questions for the moment, but the big one I want to ask you is there's a interest in getting contact information for both you, Evan and Rob.
Yeah.
So it's up to you. I can add, if you're okay with it, I could add your email addresses to the cover of the slides, and then it'll be available that way.
Yeah, please.
Okay. All right, easy enough. So great, for everybody who's asking for their contact information, the slides are currently available for download on the website. I will go ahead and pull them, add the email addresses, and then repost them within the next hour or so here. And then you can get the contact information from there. If that doesn't work, just reach out to us at DSIAC, contact@dsiac.org, and we'll be happy to make the connections. And so with that, I think we will conclude. Evan, Rob, appreciate the time, the presentation, and for everybody for joining in on this. This has been fantastic. So thank you guys.
Yeah, thank you for having us.
All right, everyone have a great rest of the day.
Thank you very much.
All right, have a good day, guys.